Okay, why don't we go ahead and get started. Today we're very lucky to have Jay Anderson speaking to us about JWST Astrometric Calibration. Jay, why don't you go ahead and get started?
Okay, great. How's the sound? Great, thanks. So I'm going to talk about JWST Astrometric Calibration. Just for some background about what astrometric calibration means is that there's distortion in almost every detector that we have to deal with. And distortion is any non-conformal mapping from the pixels to the sky. So conformal means that you can map one to another with offset, rotation, and stretch. Those are the only 4 parameters you can use. And if you use those 4 parameters, you don't introduce any distortion. But if you have to use more than that, then there's distortion in one or the other coordinate system. So linear distortion sort of comes in 2 different components. One is linear terms, which is we call them skew, which has to do with non-orthogonality of the x and y axes, or a different scale between the x and y axes. And those are distortions, even though they're linear. So it's not just a linear mapping. It's a special kind of linear mapping that does not introduce distortion. And they're also nonlinear terms. And so why do you have to calibrate it? Well, there are obvious reasons. In order to point correctly, you need to be able to put the star in the guider and make sure that your point in the detector is at the right point in space. Also, if you want to put things into slits and shutters, you need to really understand all of the distortions in your instrument. And reasons on the other end that you need to understand distortion is that if you want to combine images that are dithered with HST, if you dither by 10 pixels, there's actually, it's not just a shift. You have to shift and stretch and do different things. You have to include distortion modeling in HST, even with 10 pixel shifts. If you want to generate mosaics, so one field and then map another field that's just nearby it, if you don't have a good distortion model, that can introduce huge errors in terms of extrapolation and things. Also, if you want to do high precision analysis, like if you want to use pixels as the real constraints that they are, then you need to be able to use a very high precision distortion solution to sort of put all the pixels into the right place if you want to do a simultaneous fit for an object. With the latter thing, a differential solution is okay. With a lot of the other things, you need an absolute solution to be able to map pixels to RA and DEC if you want to do mosaicing and things like that. But for the very last one, oftentimes just having a local distortion solution is fine. For HST calibration, my thesis advisor, Ivan King, when we first started working with HST data, he was extremely frustrated with how huge HST's distortion is. And he used to always say that the people who design telescopes care an awful lot about throughput and the tight point spread function, but they couldn't care less about where the point spread function is on the detector plane. So they didn't take in, they didn't use field flatteners and things like that. And the reason, of course, is they want to minimize the number of bounces. And so distortion is just something that you live with if you want to have one less bounce. And in fact, if there's going to be any distortion at all, it doesn't really matter how much there is. You have to correct for it. All you really need is for it to be stable. If it's stable, then it doesn't really matter how much distortion there is. If there's a little bit, you have to correct for it. If there's a lot, you have to correct for it. So the only real issue is how big the correction is. With HST, it's huge. The linear terms are 9%. I mean, in a lot of the detectors, the x and y axes are off by 81 degrees instead of 90 degrees. And there's 2% nonlinear distortion. So across the 4,000 pixels of ACS, you have about 50 pixels of nonlinear distortion, which is huge, which means you can't really just look at one image and place it on top of another image. It's very hard to do these kinds of things. With HST, the calibration has been driven by necessity. The first point is it's hard to calibrate HST from the ground because you can't measure the precision of stars from the ground with the precision that you need to calibrate HST. So you can't really make an astrometric standard field from the ground that you can really use on HST. Now Gaia, of course, is good, but you still need a really dense field in order to calibrate all the nuances of HST's distortion. And so with HST, you really need to use HST to calibrate itself. The nice thing about HST is, unlike ground-based telescopes, you can take things at different orientations, which allow you a lot more diversity in terms of the things that you're fitting to each other. From the ground, you often have to take an image here and another image with north always up, which is nice for combination and things, but it makes it hard to see some kinds of the distortion. But with HST, you take observations at multiple orientations, multiple dither pointings. That allows you a lot of data to sort of do a super high precision solution. And the reason that you need to do self-calibration with HST is that HST is the only thing that can measure the faint stars that are bright in HST with the precision that HST can use them to do a calibration. So from the ground, you don't really measure the faint stars in a dense enough field to calibrate HST. And so The problem is that the calibration for HST has been driven by necessity, but necessity doesn't really allow you to do big picture things. Turns out that a lot of the distortion solutions with HST have been just improvements as needed and band-aids put on things, so that doesn't allow you a lot of long-term planning to do good science. So with HST, actually, there's a lot of foresight to do that. So we've discovered along the way a lot of wrinkles. People sort of thought that the detectors were better than they were. It was discovered that there's each in WFPIC 2, every 34th row is 3% more narrow than the others, which introduces a distortion. There was an unknown skew in WFPIC 2 until I started looking at omega sen fields and realized at different orientations things look different. With ACS, when it went up there, nobody had any clue that there would be a 68 column pattern that had a 1% impact. All of these things have to do with how the pixels were etched onto the CCD camera, onto the CCD detector. Also, the ACS skew changes over time, and we don't really know why that is. It's probably the detector is moving in the focal plane, and that's probably introducing a change in the skew terms, but nobody really knows what's causing it. And with WFC3, nobody expected this, but there are zonal errors because the same stencil was used to put the pixels on the detector, and that stencil wasn't placed perfectly. Because again, only HST can really measure positions precisely enough to see these kinds of errors, because from the ground, these things don't matter. It's hard to foresee what kinds of issues you're going to have. So you basically, sometimes you're left using the telescope itself to calibrate itself because nothing else is going to be able to calibrate it well enough. And no matter how many tests you do on the ground, there's nothing like a good star field to tell you what you couldn't see from the ground. People try to do all these measurements from the ground, but it's very hard to see all of these things from the ground. So with JWST, we decided to be more proactive. And I say we because actually it wasn't we at the beginning. It was people here before I came here who realized that this is an incredibly important issue for JWST to get right and not to have to wait 5, 10, 15 years to figure out all of the nuances. Because near-spec is very dependent upon near-cam. From the get-go, near-spec is going to have very accurate positions to know where to place stars within which slits so they can start taking images. You don't want near-spec to come online 2 years after near-cam finally gets its ducks in a row. So in 2004, when I was visiting Jeff Valenti, just as a friend, James Rhodes was working here, and he said, Jay, I've been put in charge of this astrometric field. Tell me what you think about, what do you think we should do? And so he started we talked together, and he started devising a plan. Rossi took that over, and in 2006, even before I came here, Rossi took these observations of the JWST calibration field. And when I got here, we started reducing them. And it's been an adventure since then, even before I came here. So the properties of the field, and this is sort of what I talked over with James, is you want a Goldilocks density of stars. You don't want there to be too many stars, but you don't want there to be too few stars, because if there are too many stars, they're crowded, and it's hard to measure good positions for each one. And if there are too few stars, you don't have a lot of constraints. And also you want stars that are easy to observe. You don't want there to be a lot of saturated stars. You don't want the stars to be too faint, so that you have to integrate for a long time. So you have to, you want a good number of stars that can be observed in the same field in a reasonable number of seconds. So we chose a field in the LMC because the bulge field would be too bright for JWST to observe efficiently. And so, and it also turned out that you'd like to have small proper motions so that your astrometric field is going to be good for years to come. With omega sen, the stars are moving so fast that the field wouldn't be good for very long unless you calibrate the proper motions as well. And so we picked a field in the CVZ. Also, you wanted it to be in the CVZ of JWST so that no matter when it launches, you'll be able to have access to the field. So we were able to satisfy all those things with a field in the LMC. So I have a website here. We should probably put this in some official JWST place that has several files that describe my reductions probably, 8 years ago of this field. So that's what the whole field looks like. It's 5 by 5 arc minutes on a side. It's large enough to cover one instrument, but not all of the instruments at the same time. It's at that alpha RA index. Let's see, here's the whole field, and here's a close-up to give you a sense of this separation between stars at HST resolution, which is similar to James Webb resolution for near-cam. And the other cameras are less high precision. So let's see. The star list itself, so I took all of the ACS exposures we have of the field, extracted 218,000 pretty isolated stars that you could use for good astrometric solutions. There are maybe 550,000 stars total. I didn't go to find every single star I could find, but there are at least 550,000 stars in the field, probably more. Each star is measured to about 1 milliarcsecond precision. The stars are moving at about 0.2 milliarcseconds per year. It's been, what, more than 10 years since the observations were taken. So the stars have moved maybe 2 milliarcseconds. Even though with JW we should be able to measure positions more accurately than that, we'll have so many stars that that fuzziness isn't going to be a major limitation. Even so, we might want to take an update of this field in case we just want to be able to have everything bang on from the very beginning.
So Jay,
yes?
what was your isolation criteria for the 2018?
I think it had to be isolated by 5 pixels.
5 pixels?
Yeah, that had to be the brightest thing within 5 pixels. And the other was probably brightest thing within 2 pixels or something like that.
These are ACS white fields?
These are ACS pixels, yeah.
100 milliarcseconds?
50 milliarcsecond pixels, yeah. So NIRCam is 32. So it's pretty close to NIRCam.
You suggested taking HST, which is as late in the mission, as close to JWST.
It's possible, yeah. I mean, that might not be a bad idea. And that would give us a huge lever arm on the proper motions.
Yeah.
But the second JW gets up there, we could start making our own proper motion catalog.
This was a 6-orbit, was it?
I think, how many, do you remember, Rusty, how many orbits it was? It was probably about 6 orbits. I think we took like 30 exposures and 5 per orbit. Not a vast amount of time, that's right, yeah, that's right. And people had thought before about covering a larger field with it so that you could calibrate, have the FGS, but I think at some point it's not going to be critical to cover the whole field. The reason that we designed it to be that size was so that it can calibrate the internal distortions within each instrument. And the mapping into the V2, V3 plane could be done with just a position and an angle and a scale.
And it's big enough to do the SGS to NIRCam line, but
That's right.
that's it.
Yeah, barely, yeah.
In terms of lines.
So in addition to that, I decided, I had a friend that had some time on Hawkeye, and I said, oh, why don't you observe this field? And so we have some Hawkeye data from the ground. This is the HST field, and this is J, H, and K from Hawkeye detector on the VLT. And here's what you can see. Here's a 2-mass colorimetric diagram, and there's a Hawkeye colorimetric diagram. You can see that Hawkeye is a whole lot better than 2-mass. But that doesn't get us very far. It just barely gets us down to the horizontal branch. If you look at what HST gives us, basically, this is the Hawkeye, the V with HST, and the K from Hawkeye. You can see that we only have Hawkeye data down to here. You can sort of use models to figure out what things should look like down there. So we can simulate what JWST would see of this field. These aren't a perfect fit to the model, but it'll give you a rough idea of how bright each star will be with JWST if you want to simulate the field in J, H, and K. Here's the luminosity function. This dotted line is the luminosity function for the isolated stars, and the other one is for the less isolated stars. But you can see that the sweet spot of, you don't have a whole lot of really bright stars that are going to cause diffraction spikes and problems in the field. Most of your stars that are going to be useful for JWST are here. So most of the stars are going to have really good signal to noise. So you don't have a lot of things in the way, and you don't have a crazy number of things that are so faint that they're going to cause noise in the background. So recently I was asked to put together a technical report because the people in the engineering division needed to show that they have a good plan for calibrating the telescope and all of the things that need to be done. So according to the data management subsystem requirements document, they shall calibrate the field mapping of the SI coordinates relative to a standard metric fields so that the uncertainty within any instrument is less than 5 milliarcseconds, 1 sigma per axis. So that's a requirement that they're going to have to meet, and ahead of time they have to show that they can meet it. And so Jeff Valenti a while back got together with me and said, Jay, do you think you could sort of help them check this box? So I put together a technical report showing that it should be possible, pretty trivial in fact, to use this calibration field to calibrate each of the detectors. And so the source of this talk is basically presenting you what I did in that document, and I'll have a couple of comments afterwards. So 5 milliarcseconds, which is a pretty easy precision to reach. A star in NIRCam should be measurable to 1 milliarcsecond, maybe a half milliarcsecond. Typically you can measure a star to 100th of a pixel or so if you have a good point spread function. Even if you have, that has a signal to noise of maybe 100. If you have more signal to noise than that, in principle you could do better, but you have to have a point spread function that's accurate enough to help you do that. And it turns out that in order to get an accurate point spread function, you need a lot of stars that have good signal to noise. So even if you have some stars with really high signal to noise, you don't have your point spread function with an accuracy with which you can measure that. And so at some point you're limited by a larger number of stars that you have. So really 1% of a pixel is what I claim that we can do. And that's doable, and it's actually not that hard with HST, even when there's undersampling. So 1% of a pixel for NearCam would be 0.32 milliarc seconds, which would be quite good. So in order to do the mapping, basically what you want to be able to have is you want to know if you have a pixel in NearCam, what does that map to in the V2, V3 plane? If you can do that, then you can do everything that you need to do in terms of mapping things to RA and DEC and then mapping it back to near spec or something like that based on where your guide stars would be. So the goal of the thing that I was supposed to show was just that internal calibration is going to be accurate to some number. There are other requirements that show that the absolute mapping is going to be good and done a certain different way. But as long as the internal mapping within each instrument is good, then I'm able to check this box. But in order, the instruments I think are on the hook to do their own internal calibration and the mapping with the SIAF files. So that's going to require something more than what I've done here, but only a little bit more than what I've done here. So the procedure that I decided to adopt was to sort of go halfway. So what I'll do is I'll place a feed. So in order to use this calibration field like JW is going to be using it, it's not large enough to have the guider and the detector in the dense part of the calibration field at the same time, except for maybe a couple of limited pairs. So you're going to have to put one of these stars out here in the guider, and then put the telescope itself in the dense part of the field so you can do the internal calibration of the telescope. And so I supplemented this field that I measured here with 2-mass. So all of the stars out here are 2-mass stars. In principle, we can use Gaia stars, which will have a higher precision than 2-mass, but 2-mass is good enough for what I need to do here. So I put a star in the FGS, at the center of the FGS out here, and figure out where NearCam or another instrument will fall there. So just as an example, I put this particular star at the center of FGS2, and then here's the field points for NearCam, one side, another side, that's near spec. And so this is where the center of each of those detectors would be. So if I put a star here, then that's where the NearCam detector would fall at a certain orientation of the telescope. So I'm going to simulate. Okay, yeah, so the magenta. Okay, yeah, Rosie asked me to say what the colors are. So this is just an illustrative diagram. I haven't shown all of the instruments on it, but I'm showing you the setup that I used to show how I did the mapping from NearCam to the calibration field points. And so if we put a star here at this green point, which is FGS2, then you can figure out and this is a certain V2, V3 according to the SIAF files. Then you can figure out what the V2, V3 is of all of the other stars in the calibration field if you project it about this point. So that'll give you the V2, V3 of every star, assuming a certain orientation and the pointing, which is defined by putting a star there. And that pointing just happens to put NearCam close to the center of the dense calibration field. So I have a list of stars with V2s and V3s that I know that are going to fall inside of NearCam. So the next thing I did was I figured out which stars would fall inside of one of NearCam's shortwave detector chips. So I have a V2, V3 for every star that should land inside of the NearCam detector. And I used the current SIAF files to figure out the mapping from V2 into the I and J of the detector coordinates. And that allowed me to simulate an exposure. So I have, instead of every star having a V2, V3, I now have every star with a position in the coordinates of the detector. So I can simulate an observation with the detector. Then I can simulate measuring the observation. And using the measured positions and the known V2, V3 positions, I can see how well I can back out the solution that I put in. And even though the solution that we're starting out with might not be perfect, it should have the same form, so that if I can solve for the solution that we believe to be there, if it's a little bit different, we should be able to solve for the ways in which it's different. So here's what the simulation looks like. This is, let's see, the full NearCam chip. And the picture on the right, image on the right, corresponds to the highlighted area that's in the yellow box. I used Marshall Perrin's web PSFs to simulate the field, and I actually just simulated the 10-second exposure. And a 10-second exposure, it turns out, has enough signal to noise to do everything that we'll need to do, which is very nice to know that we will not have to take really long exposures. To use HST, each of the observations had to be a fifth of an orbit. So there were 350-second exposures with HST, but with James Webb, you can take a 10-second exposure and get the same kind of signal that you need to get per star. So let's see. So what I did then is, so I took the simulated image and went through and I just blindly measured the positions of all of the stars. So for each star I have an X and Y position in the image, or an IJ position, and you can match that up with the V23 position in the catalog that I put in. So this the pair of coordinates allows me to define a linear or a nonlinear transformation from the image plane into the V3 plane. And that allows me to sort of test how well I was able to back out what I put in. And let's see. I guess I don't have the results. Yeah, the net result here, the net RMS precision with NearCam is crazy good. It's 0.099 milliarc seconds in X and 0.087 milliarc seconds in Y. So the requirement is 5 milliarc seconds. So we beat the requirement by a factor of 50 or so with NearCam, which isn't really that surprising because we have a whole lot of stars and each star can be measured to a very high precision. I just use centroids in this. You can do better with PSF fitting, but we're not going to have PSFs at the beginning, so I didn't want to sort of assume I could measure things better than we'll be able to measure out of the box. Yes?
Is deltas global or field or star dependent?
These deltas.
The deltas,
Down here?
yes. These are global for the entire field. You're basically finding a transformation. So, in which sense we are talking of distortion here?
Okay.
When I feel distortion, I need to stretch.
Well, this has, the terms here have nonlinear mappings. So, so Massimo was asking about whether I was just measuring a global orientation of the field, or whether I was doing something with higher order. And the terms here, a sub ij, x to the I, y to the I, allow up to a fifth order transformation. Yeah, so I should have mentioned that earlier. So the SIAF files for most of the detectors have fifth order transformations. Most of the power is included in the top 3 orders, and the fifth order is just there for, because it's easy to do and we might need it at some point. We never know what we're going to need. So HST has up to fifth order. And so this is a fifth order transformation. And so I was able to use the pairs of positions here to define all of the coefficients up to fifth order with a precision that allowed me to do the mapping to that accuracy. Thanks, Massimo. So the long wave channel, the short wave channel had a very small footprint. The long wave channel has a larger footprint. You can see this is the whole field for the long wave channel. And that's what a close-up looks like. And let's see, I guess with the long wave channel, I was able to get less good precision than for the short wave channel, but it's still not bad, 0.24 milliarc seconds per coordinate. We need 5, but we're obviously going to be able to do a whole lot better when we actually start taking data. But for like drizzle and things like that, they really need things to maybe 5% of a pixel. If they get things to 5% of a pixel, they're okay. But we, of course, want to do better than that. So with NIRIS, I did a similar solution, putting an FGS star in a different FGS detector on a different star to put NIRIS at the center of this high-density field. Here's what the NIRIS solution looks like, and here's what a close-up looks like. And I was able to get its mapping good to about a half a milliarc second in each coordinate, which is good. So this is what MIRI looks like. MIRI, of course, has a bigger PSF and fewer pixels. So that's what the MIRI detector looks like projected onto it. Here's what the MIRI field looks like. Here's what a close-up looks like. You can see that the PSF's bigger. I used the 5 micron filter for MIRI, so I didn't use the widest filter. They didn't say which filter, so I figured I could choose the easier filter. But the other filters shouldn't be that much different in terms of the precision. Here, the precision is not as good, but it's still a factor of 2 or 3 better than what we need out of the box. And we can do a lot better if we actually have good point spread functions and things like that. So for the FGS, if you want to measure the internal distortions within the FGS, that's one of the things we're going to have to do. So if you put one FGS centered on that point there, all those stars end up in the other FGS. And so you can use that to simulate the FGS field. And with the FGS, since it's extremely undersampled and the centroid does not do a great job measuring positions, you get results good to about 1.5 milliarc seconds per coordinate. Again, that'll get better if we have point spread functions or if we take longer exposures. And this is just one single exposure. So if you take multiple exposures, you should be measuring the same thing, but with different stars in different places. You can combine that to get a higher precision solution.
Jay, I was going to ask about that. So far, you weren't doing any
I'm not doing any dithering, that's right.
So this is real basic.
This is super basic. I wanted to keep it as easy as possible. This is worst case, exactly. And so we'll have a lot more data. We can get higher precision even just with this kind of setup.
So what's your thoughts on, I don't know if this is going there too soon to ask you, what's your thoughts on doing dithers? And we have this fine steering mirror type offset where we can just offset the telescope by 30 milliarc seconds if we want.
Mm-hmm.
And take more images.
Yeah, I mean, if you take some small dithers, you can build up a model of the point spread function, and you can get better positions from a single pointing. If you do large dithers, then you put each star in a different place of the detector, and that gives you a very different perspective of the distortion. So I would sort of want to do both kinds of things. The most important thing is probably taking large dithers so that you get multiple realizations of the distortion solution, and you're not just dependent on one particular part of the calibration field, although the calibration field should be good everywhere. So NearSpec was more complicated because there's this thing called the MSA that gets in the way of the pixels. And also the grading, it turns out, is another issue. It turns out that the current SciF only contains half of the solution. So it actually contains, at the time I did it, okay, things are changing really fast. But the NearSpec is complicated by the fact that you have one mapping from the grading and another mapping from the grading to the detector. And what angle the grading has depends on the mapping that you get to the detector. So that's going to be a complication. So I decided to just solve for this for one particular grading position. And so thankfully, I was able to get Bob Kohler had a solution from the grading to the detector that I was able to use so that I could get a good mapping of everything and simulate NearSpec. Well, it's going to be hard to back out the full model of NearSpec because you have this different angle here, and it's going to be very hard to figure out exactly what the mapping from here to here is when it's a nonlinear mapping from here to here as well. It's very hard to figure out what two nonlinear mappings are when they're sort of based on each other. But that's not going to be that important because the NearSpec people are very confident that they know the mapping from the sky to the first grading. And basically the grading to the detector is going to be what we solve for. And so that's going to be a pretty straightforward thing to do with us. So basically there will be some iteration, I think, between their solution and our solution, but in the end it's not going to be that hard to do. So the MSA itself, how did I deal with that? This is a ×10 resolution simulation of what the MSA looks like. These light gray bars correspond to image pixels. So you can see that the MSA blocks out a reasonable fraction of light in some pixels. So that's a challenge to deal with. So what that does is it ends up, if you're measuring centroids then, and a star lands here, then some of this light's going to be blocked out. So the star is going to look like it's over here instead of where it actually is. So that's just something that you have to live with unless you model the heck out of it and try to do everything right. I'm just trying to do things simple with centroids. And so I just used centroid positions and decided to just live with that kind of error that comes out of it. I actually was able to look at some thermal vac data where they took two dithers, one observation and another dither with maybe 100 sources. And it turns out that the size of the centroid shift that I was seeing, typical of a star, is the exact same centroid shift that they saw with their thermal vac test. So that sort of says that the impact of the light blocking of the grading is much greater than any kind of diffraction effect that the grading would introduce in the positions of stars. So that's nice to know. So this is a relatively realistic simulation that I'm doing. Here's what the grading does. So you have the whole 2048 by 2048 NearSpec detector, but if you are in just imaging mode, you only get light over some fraction of it. So you actually can't solve for the distortion in this part of the detector very well because you never get any light there. But you don't need to solve for the distortion there. So here's what I did. So I put a guide star centered on the FGS here. That puts the NearSpec, one of the detectors, mapping into the calibration frame here. So you can see the calibration field isn't that much larger than we need to calibrate NearSpec, for instance. It's just about the right size. So these red stars are the ones that map onto the detector itself. And the yellow stars are the ones that get mapped onto, they get blocked before they can make it to the detector. So here's what an image looks like if we didn't have the grading on there. And here's what the image looked like if you do the throughput modeling. And I did that at a factor of 10 resolution. And so you can sort of see that it's not a very pretty image. And here's what just the throughput itself looks like. So you can see that the throughput is introducing a very large impact on the image. And here's what the whole image would look like if there weren't any grading or blocking there. And here's what the image looks like if you consider the blocking. And it turns out that since it's going to be hard to solve for the distortion over here, the field points in the SciAF files are centered like here, which makes it hard to solve for the solution. I decided to just do a local mapping, which had the center here, and allowed x to go from -1 to 1 and y to go from -1 to 1. That was the easiest way to do the mapping, since I didn't have to solve for the absolute mapping in the polynomial that SciAF is going to use. I just had to show that it's doable. I did it the easy way.
Could we use points in the center? We have points in the center of each of the MSA quadrants. Would they have helped? Like at the center of each of those two squares.
That's what I did, yeah. That's what I did in the end. But I think the field point is here for near spec.
We've got a few.
Yeah, okay. So it's not a big deal. But in the end, I was able to get a mapping that was good to about 2 milliarc seconds per coordinate, which is good enough for requirements. And this was just with one single pointing. So if you take 2 pointings, you can do root 2 better. 3 pointings, you can do better than that. So this is just showing you that it's going to be very, very easy to meet the requirements.
So AJ, so I'm sorry, so you have unique separate and disjoint polynomials for each quadrant? Or
No, for each, no, I just had one polynomial to describe this whole region here.
You have a polynomial
So,
to describe.
yeah, Matt was asking whether I had a separate polynomial for this detector chip combination and this, or this MSA chip combination and this MSA chip combination. But no, I just had one for the two together. But the nonlinear terms aren't that large. So either way you do it, it's going to be doable. So it's just a question of how do you want to set it up in the end. So the main result of my technical report that I'm describing here is that all limits instruments and detectors should be able to calibrate the internal distortion to much better than 5 milliarc seconds per axis, just with a single 10-second exposure of the calibration field. And that's what everybody is, very happy to see. In actual commissioning, it will take some iteration to, if the field point is not exactly where the SciAF file now thinks it is, in order to do my mapping from the FGS position to V2, V3, get a unique V2, V3 for every object, and to match that to the field point, you need to do some iteration in the projections that I was doing. And so I didn't want to try to do the whole solution for not just the nonlinear mapping, but for the orientation and the other things. Also, there are some assumptions when you have these polynomials. The polynomials can deal with orientation and scale as well. So you have to make some assumptions about what terms you want to be zero in your polynomials, because in addition to having that polynomial, you also have a rotation and a scale. So those are done sort of redundantly. So I didn't know exactly how they had defined their polynomials, and there was no point in me trying to re-engineer everything. So I just wanted to show that the nonlinear distortion within each detector could be solved for, and it can. But when people actually do this, they're going to have to take these things into account. So additional benefits of the observations of the calibration field are, one of the things that people had in mind for a long time is long-term calibration validation. So if we observe these fields every few months or every year, we're going to be able to monitor the photometric through point, the astrometric stability, the distortion stability, all these other things. Also, we'll get improved astrometric calibration beyond what's doable here with self-calibration, which means if you use JWST observations to calibrate JWST, then the stars that you need to have high signal noise will have the high signal noise that you need for the calibration. So using HST, you have to take crazy long, deep, well, not crazy long, but relatively deep HST observations in order to calibrate JWST. But to calibrate JWST, you just need to take 10-second observations. And so JWST is much better matched to do its own calibration, but you don't want to have to start that way. So also, if you do improved astrometric calibration better than 5 milliarc seconds, then there's a lot of science you can do with the mappings that enables. Another thing that is going to be doable right out of the box with these observations is if you take some large dithers, you can do a calibration of the L-flat, long-wave flat field components of the calibration files. And so you basically observe the same stars at different places of the detector, look at their throughput, and you have a very dense array of constraints that allow you to really tie down the photometric sensitivity as a function of location on the detector. Also, something that's close to my heart is that we can extract PSFs if we observe this field with a couple of dither positions. There are a lot of bright isolated stars in these images, so it'll be very easy to get empirical point spread functions that can be used for science. We could measure the full field dependence of the PSF. And I should note that there's a new HST effort going on with the UVIS team and the ACS team to get really accurate point spread functions so that people can start using them for science. Now, there's a reason that it hasn't been done so far. You think HST's been up there for 25 years. Why haven't we done this before? It's hard for people to actually use them because PSFs are really only best used in the FLT, the raw detector frame images. But it's very hard for people themselves in their science to use those images. I've done a lot of my science with that, but it's taken a lot of effort on my part to learn how to do the mappings correctly and how to measure PSFs and how to use them. And it's a real challenge for normal people that don't have 5 years of a postdoc to devote to that to understand it. We're trying to bring some of those tools to people so that they can start using them. But in order to do that, you need to do a lot of things at the same time. You have to do the distortion mapping to a precision of better than 1% of a pixel. You need to know how to register one image with respect to another image to better than 1% of a pixel. And that involves measuring objects that you can use to find the exact offset between images because the postargs aren't necessarily that accurate. You also have to have good point spread functions that allow you to do that kind of analysis. So you have to combine all three of those things together if you want to start using the pixels as the real constraints that they are. You know, a pixel is just a constraint telling you that this amount of flux landed within this boundary, within this wavelength range. And so that's the only constraint we really have on the sky. When you drizzle things together, you smear out some of that information, and that makes it much more difficult to know, to get the full constraint that you could have if you went back to the original pixels. But there's a reason people haven't done that before. So our hope is to do this for HST so that it will be easy to do it for JWST, but also so that people will be used to thinking of what they can do if they can actually use real constraints. So astrometry with JWST, just to give you some general background, it should be similar in precision to HST, maybe a little bit better with NIRCam shortwave channel, maybe a little bit worse with some of the other detectors, but it's going to be extremely good. The reason that HST has such an advantage over the ground is severalfold. One is its precision is better, but from the ground you can get this kind of precision with isolated stars. HST can observe really faint stars. You know, so when you have a high resolution, you spread out the background of the light over a lot of pixels, but you concentrate your source. So you can go really, really faint, and you still get extremely high precision position measurements. So HST has a sweet spot, say between V of 18 and V of 24, where it can get extremely good astrometry. And from the ground, you can't do that kind of astrometry with the plentiful stars that are at those brightness levels. With JWST, we can go even fainter than that, much fainter than that, and the sweet spot will be even wider because it'll be all up the ramp detectors, so we don't need to worry as much about saturation. So there's a lot of stuff that JW will be able to do, sort of going beyond what HST can do. And it's nice to know that it takes only a couple years to get a good baseline with even HST or JWST. There's a lot of science you can do in just 2 years. And even less than 2 years, actually. Field stars are moving. You can see field stars moving within a few months. So another thing that can be done is image combination and mosaicing. If you have stars, you can define the transformation between one image and another image extremely accurately. If you have to use galaxies to do that, then the handles are fuzzy. And that's one of the reasons people haven't used the FLT images as much as they could, because it's been very hard to do the mapping from one image to another or from a set of images into a reference frame with accuracy. If you have a good PSF and you know you're dealing with stars, then you can know exactly how accurate your mapping is from a pixels and an individual exposure into the reference frame. And that allows you to do a lot of things that people haven't been able to do thus far. Let's see. So there's a reason that drizzle is blind to errors of 5% of a pixel, is that when it combines, I'm not trying to say bad things about drizzle. I think drizzle does great for what it's supposed to do. It's supposed to preserve flux very rigidly and put it very close to its original position. But there's no way that it can resample the pixels in a way that allow you to do high precision pixel-to-pixel type measurements. You really need to go back to the FLT images to do that. And so there's a reason that drizzle is blind. You know, if you have the registration good to 5% of a pixel, then drizzle doesn't care. And the reason is that drizzle can't do much, you know, with super accurate things like that. So if you do PSF fitting on drizzled images, you're going to get errors of 2, 3, 4% of a pixel. And there's just no way you can get around that. So differential astrometry, internal motions in clusters, obscured clusters where you can only see things in the infrared, gas dynamics, motions of gas features, all of those things will be easy to do with JWST when you have good transformations. Absolute proper motions with respect to background galaxies, we're starting to do that with HST now. It's easy to identify, if you have a good point spread function, it's really easy to identify what a star is and what a galaxy is. You almost never make a mistake because even the faraway galaxies with HST are not point sources. Unless they're, you know, a super bright nucleus on top of a galaxy, That's the only case where galaxies look like point sources. Super faint in the ultra deep field, you can tell the difference between stars and galaxies. It's almost amazing how well it works when you have a good point spread function, because galaxies are going to be maybe 2 pixels in size. And it's very easy to tell something that's 2 pixels in size from something that's 0 pixels in size. And so when you have good point spread functions, it opens up a lot of things that can be done in terms of science and other things. But when you know things are galaxies, you know that they're not moving. So if you can get a reasonable position for them, then you can do absolute astrometry. And there are field stars in every single exposure. So there's going to be a lot of stuff that can be done. I'm working on some HST projects now using basically fields that HST has observed twice. JWST will be able to do the same kind of thing, but even better. So I think this is my last slide. So I just wanted to talk about some high-level products. HST doesn't really, has sort of asked for permission to create high-level products, but we haven't gotten permission to do that, so we're kind of limited in terms of what we can do, because we're on the hook for creating drizzle products, but not on the hook for creating catalogs and things like that. People have created catalogs, but it's sort of a side production rather than an official instrument team production. And so JWST is on the hook for high-level products. It's not clear exactly what high-level products JWST will be producing, but JWST will be allowed to produce source catalogs and things like that. So it's good to start thinking about that. And some of the tools that we're making for HST that we're starting to sort of make on the side for HST will be things that can go into production for JWST. So we can sort of play around with things on HST even though we can't go full production with them. And with JWST, we'll be able to just start using them and actually have funding to do them the way that we'd like to do them. So I think it's good for people who are working on JWST to be thinking about what kinds of high-level products you might want when you have good point spread functions and you have good astrometric registration between images. Let's see. So we should I'll go very briefly, we should be able to give good empirical point spread functions to people that can predict the fraction of light in a pixel to better than 1%. That's pretty easy to do. Harry Ferguson and other people are working on producing some tools for the community that use point spread functions to do different kinds of analyses. It's hard to produce a tool that does everything, so you end up producing tools that do specific things, and people end up having to mix and match tools. But Harry's been doing some Python coding sprints to try to figure out ways to use point spread functions and the kinds of analyses that people will be doing. Also, I mentioned before that source catalogs is one thing that JWST is going to have to produce. Exactly how it produces them is sort of up in the air, and we sort of get to define that at some level. So, source catalogs are good for mosaics, and that's what the Hubble source catalog right now is doing. It's being done on people's science time. But it's possible to take the drizzled stacks and create source lists from them, and they've done a lot of really good stuff with that. But you can get a considerable improvement in precision when you go back to the individual exposures to measure positions and then combine the positions together in a source catalog. So you can get the full astrometric and photometric precision of an individual exposure if you go back to the original unresampled images. And that allows you to get empirical estimates for position and flux. So you have a catalog and you know exactly how accurate this position is, exactly how accurate this flux is, because you have 10 different measurements of each of them. So that really allows you to know things. Discrimination between stars and galaxies. It allows you to fit faint sources and undersampled images if you do forced photometry. In an undersampled image, you get a lot more signal to noise if the star is centered on a pixel than if it's at the four corner between 4 pixels. And so you can use that kind of information to optimize your measurement of faint objects, or faint stars especially. One of the things that I looked at a while back was this thing I called them pixel bundles. So if you have a source that you're interested in, you can collect all the pixels within, say, a 10 by 10 pixel region of that source and put it into one place. And each pixel, if you have a mapping from each individual pixel into a reference frame, you can use all those pixels together to constrain whatever you want to measure in terms of the shape of the object, the brightness of the object, the position of the object. It's a convenient way to sort of put everything together and not sort of have to go to different images and then worry about the transformations while you're trying to do science. So that's something, these are just ideas that people could run with, and having good astrometry is sort of the thing that opens up all of these possibilities. So that's it.
Are there questions here in Bacall Auditorium for Jay?
Massimo.
Two tiny things that one is that the distortion that you are measuring affects also the shape of the PSF.
Mhm.
And seems, I think there is the same PSF scattered across the field
That's right.
without any PSF variation. So the question is how much this may affect the results. And the second one is about relativistic aberration.
Mhm.
I understand you're observing at the North Pole
Mhm.
basically of the orbit, so this may be a small effect. But this is of any relevance working with very crude images.
Okay, so he asked two questions. One is that the PSF varies across the field. How will that affect what I did? And the other question is if there's velocity aberration, that's going to change the image that you get on the detector, and how will that affect things? So the last question, I'll answer that first, is the velocity aberration just changes the plate scale at 1 part in 10 to the 5 or so. And so that's a correction that's very easy to get from the engineering data. So that doesn't, you get the sampling that you get based on that, but when you map the pixels into a reference frame, that's when you can take that properly into account. And so if you take that into account, then you can measure the plate scale accurately and all these other things. As far as the PSF varying across the detector, sort of there's a degeneracy between how you measure the center of the PSF and how you measure the distortion solution. So you could define the center, if the PSF could be here and you define its center to be here, and that's a legitimate thing to do, but it's kind of crazy. But when you deal with undersampled PSFs, exactly how you define the center is you have to decide on the convention. It's not obvious how you define the center of a PSF. Is it the center of light if you have an asymmetric PSF? Is it the center of light, or is it the peak of the flux of the PSF, or is it some full width half max center or something like that? There's no obvious way to define the center of a PSF, so you just have to adopt a convention. And whatever distortion solution you come up with should be consistent with that convention. And so I just didn't include the mapping of the changing of the PSF across the field because that would just sort of fall back into the distortion solution that I was trying to measure. Does that make sense? Is that? Okay. These are the kinds of things that you have to think about when you try to do these high precision modelings of point spread functions. And it turns out that with ACS, the distortion is so great across the field that the angle of the diffraction spikes changes on an FLT image by like 3 degrees. So if you're trying to model all of those kinds of things with the PSF, it's complicated. That's why I do all of my PSF modeling in the image frame rather than the V2, V3 frame, because it's easier to deal with that way.
So Jeff, I guess your report shows you're easily meeting the requirements.
Yes.
5. I mean, 5 is just somebody pulled that out of the air.
That's exactly right.
And you're actually meeting them at the basically 1 or 2 milliarc seconds.
That's right.
So a couple of things. I mean, first you've got this catalog now, which is, as you've said, it's degrading in time because it's Epic
2006, yeah.
2006. So it'll be on the order of 13 years old by the time we actually get to use it.
That's right.
And so now the catalog errors itself will become the dominant source in the
Yeah, we have some
residuals.
observations from 2011 that Linda Dressel took that we could use to determine proper motions, but the proper motions are only as good as the difference between positions at the 2 epochs, and so that would be degrading as well. That's right.
Yeah, that's a good point.
So it might be worthwhile getting a refresher.
Yeah.
And we wouldn't need to do it crazy. You wouldn't have to be super close to JWST, because the error in the positions is going to go as it's going to be very small.
No,
if
right,
it's
right.
2 or 3 years, we can extrapolate the proper motions.
This year, next year would be great.
That's right.
Yeah. And so, and the other one I wanted to mention was you were talking about PSF modeling and such, and like with JWST now, we can actually do offsets that are a milliarc second.
That's right.
Up to 60 milliarc seconds. You choose it.
Mm-hmm.
Can you imagine can you talk about how it might benefit if you have one observation followed by another one that is shifted only by, say, 10 milliarc seconds in X or Y or both? Yeah,
I mean, it turns out that the size of the PSF doesn't vary at 10 milliarc second level. It only varies according to the size of the diffraction ring that you get for the halo of the PSF. So dithering by like 1/100th of a pixel accurately isn't going to tell you that much more about the PSF.
Okay. That
you're not going to know by dithering 1/10 of a pixel or 25% of a pixel. So you're not going to learn that much more if you can place things super accurately like that. Even if you have an object that's resolved, by taking a little shift like that, you're really not going to explore very much because most of that is just completely expected from the shape of the PSF.
Okay. But again, I just mentioned 5 as, you know,
Yeah.
we can go that little, but we can also do 60.
Yeah.
And I
Yeah,
think
having
60
accurate,
is, you know,
having
is,
accurate dithers is useful, of course. Being able to dither accurately. That's sort of with HST, we don't have that precision.
yeah,
And so it's been hard for Drizzle to sort of recombine data products. It sort of has to assume that the pos targs are as accurate as it wants them to be. And in the end, there are some inaccuracies that it has to live with unless it goes through and does a tweak reg iteration, which is complicated, and that's not done in the pipeline for HST. But if the dead reckoning pos targs are better than that, then the Drizzle products will be better than that. In the end, I think people will want to include Gaia to get the absolute registration done well. If you have sources within each exposure, then you can do a super high precision absolute astrometric solution. And there's obviously working groups now planning to make that work for JWST. But for the differential offsets, we're going to have a lot of stars. So if we are able to use point spread functions to identify stars and to do this as part of the pipeline, then I think we're going to get much better registration. And starting out with good registration makes everything easier.
sure. You know, the instrument teams are actually writing their APT files at this time as part of the whole PIT process for the commissioning to actually go and observe this field. So, you know, I think there should be some attention to details that the data are actually acquired.
Well,
correctly.
exactly. Yeah, that's
Yeah.
right. And so the nice thing about JWST, I should have mentioned when I got the SIAF files from Matt, I realized that the JWST distortion is going to be nowhere near as bad as HST's distortion. So that's a very good sign. So it's very, very small compared to HST. So we're not going to have these huge distortions in the field. So we'll be able to dither over reasonably large distances and still have a tight dither pattern that's coherent at the edge of the frame, which should make a lot of things easier. With HST, you sort of had to dither less than 10 pixels. Otherwise, your pixel phase coherence at the outer part of the field is messed up. So that really limits what you can do with HST. With JWST, we won't have those issues.
That was mainly because of the linear terms, right? The skew.
No, that's
as
because of the nonlinear terms. The
the
linear
high
terms
order.
wouldn't cause problems. It's the
Oh, okay.
nonlinear terms. But the nonlinear terms are 50 at the edge of the frame. So that adds
Oh,
up pretty
right.
fast.
Oh, okay, good.
Are there any other questions for Jay here in the room? If not, let's see if there's any questions online. If anyone online has any questions on WebEx, please feel free to unmute yourself. Everyone's on mute, and go ahead and ask your question. I don't see any questions online. Okay, well, if not, let's go ahead and thank Jay again for his presentation. Thanks.
It's going to be fun.
And we're going to have another JWST community lecture in 2 weeks, in which time James Miserol is going to talk about the NERSPEC MSA.